So the problem here is a two-particle problem. You have one nucleus and one electron. Did I start the broadcast already? I did. Yeah, I did. Okay. All right, so the energy associated with the center of mass then is essentially, what did we say? Essentially that of the, this is the energy of the nucleus. We say the translational energy of the atom, the movement of the atom as a whole. You just track it at the center of mass, which is essentially located at the nucleus. Okay? The energy associated with the reduced mass is essentially that of the electron. So this is the electronic energy. And the Hamiltonian for the reduced mass is basically the Hamiltonian that will only depend on the electronic coordinates. Okay? And what would our potential energy look like? What's the potential energy of interaction between a proton and an electron? Depends on the distance. Coulomb's law, right? Force is 1 over 4 pi epsilon naught Q1 Q2 over R squared. And potential energy is, remember from early this semester, charge of the nucleus, which is plus ZE, times, I forgot my factor in front. Potential energy depends only on the distance between the nucleus and the electron is 1 over 4 pi epsilon naught times charge of the nucleus times charge of the electron, which is negative E over R. Okay? What does this plot look like? What's E, by the way? Charge of electron is how much? Smallest unit of charge? 1.602 times 10 to the negative 19 coulombs. What would that potential energy look like? So this is the energy. If I were to plot potential energy versus distance, this is R going to infinity that way. What would it look like? First of all, is it positive or negative? There's a negative there, right? So the potential energy plot is going to look like this. So V of R approaches 0 as R approaches infinity. So it's going to approach 0. So this is 0 right here. And V of R is going to approach negative infinity. Right? If R becomes very small, your potential energy goes to negative infinity as R approaches 0. Okay? What does a negative energy mean? Nothing. It's because energy is really relative. Okay? Basically, what are we saying here is that if the electron and the nucleus are infinitely far away from each other, we define that as potential energy equal to 0. Remember, potential energy, you can set that to any value for any reference point. Okay, so it's just a matter of convenience. We're going to set our potential energy to be 0 when the electron is very far away from the nucleus. And so let's pretend we have an electron that has, let's say, this much energy right here. Okay, let's say this is the total energy of your electron. Okay, let's say your electron is over here at this distance and moving to the right. What's going to happen? Classically, let's take a classical description of this electron. This is the total energy, so what is this difference between potential and total? That's your kinetic energy, right? So the electron is moving away from the nucleus. Is it going to feel a force from the nucleus? Is it being attracted to the nucleus or repelled by the nucleus? Repel. Repelled? Attracted, right? Opposites attract. So as your electron moves away, it's going to feel a force pulling it back towards the nucleus, right? So as it moves away, what's happening to your electron? classically you'd say your electron is going to lose kinetic energy. It's going to slow down. So moving away from something that attracts it, the electron is potential energy, we say, is rising. Its potential energy is rising means its kinetic energy is dropping. It's slowing down. It's moving away from something that's pulling it back. So it's going to slow down. Eventually, what happens to the kinetic energy? Becomes zero. All the energy becomes potential. At this point, what does that mean? The electron stops, right? Classically, that's what it means. So if the electron has stopped, will it stay stopped? It's still being pulled. So it's going to accelerate backwards, back towards the nucleus. And what happens? Kinetic energy is going to start increasing again, increasing, reaching infinite kinetic energy, and it's just going to crash into the nucleus, never to come back. So it seems like classically, if your electronic energy is less than zero, there is no way your electron can survive outside your nucleus. It's going to crash back into the nucleus. Right? So the atom as we know it, where your electrons going around the nucleus, cannot possibly exist. This is one of those problems that were brought up when Rutherford's experiment led to the notion of electrons going around in circles around the nucleus. Okay? Added to the fact that even, okay, now we're talking one-dimensional motion here, but even if you're doing three-dimensional motion, it's still going to crash into the nucleus. And one of the other things that's known is that you have electron going around. If you have an electron going around in orbit, okay, it's accelerating. And any charged particle that accelerates is going to generate electromagnetic radiation. And if it generates electromagnetic radiation, it's going to lose energy. So eventually, any electron going around the nucleus is going to spiral back into the nucleus. So in this sense, we say classical mechanics is wrong. It's inconsistent with reality that you've got electrons going around nuclei all the time. They don't crash. Okay? So anyway, when energy is less than zero, we say we have what's called a bound state. Okay. Now what happens if energy is greater than zero? Up here. Let's say you have an electron moving this way, heading out away from the nucleus. What will happen? That's your kinetic energy. As it moves away, what happens? Kinetic energy gets smaller. It's still being pulled back, right? Eventually, what's going to happen? This red curve eventually is going to approach zero, right? You're still going to have some residual kinetic energy left. So the electron is just going to keep moving away from the nucleus until the nucleus is so far away that it hardly affects the electron, and at which point the electron will start moving pretty much at constant speed, never to return. What if the electron happens to be moving back towards the nucleus? Then, just like before, it's going to crash into the nucleus. But at least if it's happens to be moving away, then it will be able to escape. In other words, E equals 0 is the minimum energy that an electron needs in order to escape the nucleus, provided it's moving away from the nucleus. Okay, so anyway, if you have E greater than 0, if we were to treat this quantum mechanically, you'll have what's known as continuum states, just like your free particle, okay, except that the potential energy is not constant. And when you have energy less than 0, you have what's called bound states, and we'll be solving for the allowed energies for the bound states of our electron.